All right, this is part 2 of the linear algebra review, and let's actually review a couple of things on vector and matrix notation. So I do actually have a class roster here, so I'm going to attempt to remember or meet you all and remember your names. So it's Kevin Grover. So Kevin, if I write a vector in this form, 1, 2, 3. How do I call this type of a vector? We have two types of vectors, or arrays of numbers. So I can write them in this. It's 3 times 1 actually, okay? But it's also a column vector, right? So this is a column vector. How would I make a row vector out of it? What is the operation? So I would just write it as a row, and the operation, it's called transpose. So let's call this U. Then U transpose is simply a row vector, 1, 2, 3. Of course, if I do it again, what would be U transpose transpose? It'll be U. So I go back to U. Okay? So don't get confused if there's multiple transpose, just keep doing it, and there's actually some examples like that in the homework that will be assigned today. Okay? So now we had certain vectors, so we had certain measures or norms on those vectors. So is Leonidas labeled? So Leonidas, am I saying this right? You go by? I go by Luke. All right, that works. So again, if I mispronounce your name, you can always mispronounce mine. There's plenty to mispronounce there. So we actually had certain measures here. So what would be a norm of this vector? What do we mean by norm, and what do we use norms for? Okay. So this is a vector 1, 2, 3. We can imagine this is a position in 3-dimensional world. So I would go 1 in x, 2, and 3, okay? And then I have a vector that goes from the origin of my coordinate system to this point, 1, 2, 3, right? So if I have a length of that vector, that is actually a norm, okay? So that is sort of the magnitude of the vector. So I'm trying to figure out how to measure a vector, which is this multi-dimensional thing, okay? I'm trying to pin a number on it so I can compare it to another vector. Otherwise, if I have a vector like this and a vector like that, well, how do I compare them? Who is bigger? Who is smaller? How, right? So I can find a measure of it, and those measures we call norms. So vector norm, the simple one, vector norms. The simple one, which would be basically equivalent of the length, okay? And it's also called Euclidean length because Euclid in Greek geometry back in the day came up with the concept first. We're also calling it L2 norm. Do you recall possibly how do I compare that? How do I find for 1, 2, 3 what is my length? Okay, so the formula goes like this. If this is my U1, U2, U3, I basically take squares of all of those numbers, sum them up, and then take a square root. Okay, so this would be in 3 dimensions, but I can do this in general for x vector that has x1, x2, all the way to xn. My norm 2, so this is L2 or Euclidean norm. Is square root of x1 squared plus x2 squared plus all the way to xn squared, however many I have. So again, in 2 and 3 dimensions, this is the length as we know it, geometric length. But in multiple dimensions, I can still do the same thing. Okay. Now, is Niklaus Davis, Nick, here? No? Valerie? So Valerie, what would be a 1 norm, do you remember? Okay. So instead of squaring numbers, what can I do? Just add them up and we'll actually add absolute values. So my one norm of u, I'm going to go back to this example, u would be absolute value of 1 plus absolute value of 2 plus absolute value of 3, which in this case is obviously 6. There is one more, and this will be the 3 most common norms that we're going to use. I'm going to denote it as u infinity norm or max norm. It's simply going to take the maximum between these numbers. So absolute value of 1, absolute value of 2, and absolute value of 3. So maximum is obviously 3. So obviously I can see that I have different numbers. So in this particular case, I would have a square root of, we never computed it. So square root of 1 square plus 2 square plus 3 square. 3 square is 9 plus 4 plus 1, that is square root of 14. So I have 3 different numbers, square root of 14, square root of 6, square root of 6 and 3. Okay? So I have different measures. And which one do I pick depends on what is the application that I'm doing. So if I have distance that is just geometric length of the vector, okay, I will do that if I can fly from place A to place B, okay, then I can take that as a distance. But if I actually have to walk on a grid in a city, okay, essentially this norm is kind of counting the number of blocks I had to do if I'm looking at a two-dimensional example, okay? So basically norm 1 makes much more sense. If I'm actually looking at the long numbers, such as, or for instance, we have bell logs, okay? Then if I have just take the numbers, if I have a small number next to a large number, say 0.01 next to a 30, okay? Then if I do square of that small number and square of the large number, the square of the large number will eat the small number away, okay? I'm not going to be able to basically see them, see the small number next to a big number. So in the sum, this small number will not contribute a lot. This smaller number will contribute more if I just sum up the absolute values. Okay. It's still going to be smaller than the larger number, but it's going to overall contribute more. So I might want to be careful in which norm I pick, depending on my application and what it is that I want to accentuate. Of course, this max norm, or L infinity norm, so I'm calling them L1, L2. So this is L1 norm and L infinity or max norm. This is kind of picking out the outlier, picking out the maximum number, whatever that maximum is. Okay? So that might actually make sense in the application I'm looking for. So this is quick review of the norms. Another thing that we did, let me just save this. Did everybody have a chance of writing this down?
So just to reiterate, that double or single means one?
Yes. So it's sort of pointing out that the x you're dealing with here is a vector or an array rather than an absolute value of it. Okay. So basically we're distinguishing between an absolute value and norm of a vector. Because this one is basically a generalization of absolute value, but this norm is not a generalization of absolute value, so it's kind of to distinguish the two. And these little numbers, you can technically omit them if you know which norm you're talking about. But if you don't, then you have to place them to be clear. So typically also when we actually often, when I'm just looking at the direction, so I have a velocity vector, and I just we often normalize it to something that has norm 1. Okay? This normalized vector is called unit vector. So unit vector, I'm going to change color here. Before I move on, I'm going to define it. So unit vector, u, and I'm just going to say u hat just to distinguish it from u, is norm. I can, of course, do this in the norm that I'm interested in. I'm just going to do this in the 2 norm. So if I divide u by square root of 14, what is going to be my result? Let me meet somebody else. Maya, answer? Did I say that close to correct? Yeah. Okay. So, Maya, what will be? How will I actually divide this by square root of 14? Will I just divide the first element or all of them? All of them. So we immediately actually define how do we do scalar and vector multiplication, or in this case division by a scalar. So I'm going to work on every element. So if I'm dividing by square root of 14, I'm going to divide all of them. Okay, and this is my result. So this is a vector that has geometric length 1, L2 norm 1, Euclidean norm 1, however you want to call this norm. Okay, all right, let's move on a little in our examples. Okay. So one operation that I'd like to do, or with scalars, I know how to multiply, divide them. I know how to add and subtract them, and now I would like to add and subtract vectors as well. I would like to do certain operations. Again, why we need vectors and matrices is we need them to store the data, and I would like to do efficient manipulation of that data, which involves basic mathematical operations. So if I have 2 vectors, let's see, let's meet somebody else. William Wrong? William here? No, he's not here. Michael then? So Michael, if I had 2 vectors like this, let's say, one, I'm gonna stick to this 1, 2 business because it's easy. And if I had -1, 0, 1, can I do this operation? No. So I have to have same number of elements. So basically, let's modify that. So I'm going to modify it to be able to do it. And let's make it more fun. So I'm going to do 3 times -1, 0, 1. How do I do this? What is my result?
You get 1 plus -3 for the first number, so you get -2, and 2 for the second number, and then 3 for the last one.
Okay. So basically I'm gonna, and even if I had the multiplication here, I would multiply each element and just perform the addition, and my result is the vector of the same size. So this is called linear combination of vectors. Yeah, linear combination of vectors.
I think your thing's weird.
Oh wow.
Yeah.
Okay, undo. I pressed this inadvertently. Wow. Okay. I'm gonna kill this, whatever it is. So I placed this some sort of a mirror that basically wrote as a mirror. So there are all these little, this sketchbook and this tablet is actually used by artists a lot. So there are all these like types of things that I would never think of doing in a classroom. But I could actually do mirror images and whatnot. So I'm definitely underutilizing my tool here just by doing plain writing. Alright, so this is linear combination of vectors. And one more thing that I want to note here is that when I create this vector from two other vectors and just add them up, this vector is called linearly dependent on the first two. Okay, so that's just sort of a notation. So this vector is linearly, so the result is linearly dependent on input vectors. In essence, that's pointing out that I'm not adding any new information, I'm just manipulating the old information, and that's often important. Okay? All right, so now we will just quickly go back to a couple of more definitions, and I will continue writing after this, and I will also possibly see if I remembered to, if I forgot to review anything. And I have one more fun examples with norms, which is a bit coming from a little bit of math theory. But the question for you here is, how many circles do you see? Is this a circle? It is. So this is the circle in the classical sense. Definition of a circle is that all points on the circle, right, are radius 1 or distance 1 from this central point, right? So this distance is 1, this distance is 1, this distance is 1, or whatever radius that I pick for the circle. In this case, I have radius 1. Well, this distance is a norm. Okay? So I could actually change the norm. So I'm actually wondering, what would circle look like? And circle is a geometrical location of all of the points that are distance 1 from the origin if I change the norm. So let's look at norm 1. If I had point 1/2, 1/2, what is norm 1 of it? Come on, it's 1/2 plus 1/2. So it's 1/2, 1/2 on a circle of radius 1. Yeah. So that's actually this point right here. Okay. This point is a 1, 0. 1 plus 0 is 1. So that's on a circle as well. 0, 1, that's on a circle as well. -1, 0, absolute value of -1 is 1, plus 0 is 1. That's on it as well. -1/2, 1/2, that's on that circle too. Actually, all of the points, this is a line 1 minus x. This is a line y is equal to 1 minus x, right? All of these points are on the circle of radius 1 if my norm is 1 norm, L1 norm. It's kind of cool that this is actually how a circle looks like in this norm. Just as a geometrical point. For infinity norm, let's look at this point. Okay? This point here, 1, 0. Maximum of the absolute value between 1 and 0 is 1. So this should be on the radius 1 in max norm. Okay? But so is any point here. Because between 0, if my y coordinate is between 0 and 1, then my x coordinate, which is 1, is larger. Okay? And that's my max norm. So all of these points, right, are on the circle of radius 1 in max norm. Does everybody see this? And I will do the same along these lines. So this is how a circle looks like in max norm. Yes? The second one, actually, I'm going to give myself points here. So this is sort of on a, so let's say that this is 1. Okay? So pick any point here, right? This point is 1/4, right? Is it? Do you agree with me? It's 1/4. This point here. What is the maximum between the two? 1. So radius of this in max norm is, it should be on the circle of radius 1 in max norm. So then I look at this point here. This is 1/2, 1. Maximum between the two is still 1. No, I'm talking about the, so I'm actually walking around this perimeter, and that's precisely this. Make sense? So actually for every point here, coordinate 1, they all have x coordinate 1, and that's the maximum between the two. Here, for every point here, they have y coordinate -1, absolute value of it is 1. So in absolute sense, this y coordinate is larger than any x coordinate that I have on this portion. So that must be on that circle too, and that's how I go around. So that's my circle in max norm. Fun? Looks like I'm the only one who has fun here. Yes. Huh? And second one, this is norm 1. So here again, this is 1/2, 1/2. Absolute value of 1/2 plus absolute value of 1/2 is 1. Absolute value of 3/4 plus absolute value of 1/4 is 1. And so I go around the circle.
Wait, so just to make sure, so you're basically, your two right diagrams are based on the points from the left diagram, except you're just looking at the values a little bit differently.
So yeah, I'm just looking at different norms. So this is a circling norm 2, this is a circling norm 1, and this is a circling norm max norm or infinity norm. And circle is defined as all of the points that are norm 1 away from this center. That's one definition of a circle. A little to stretch your imagination. Alright, this was just for a little bit of fun. Okay, so let's go to something a little more dry. In general, I can define norms in all kinds of ways, and we actually define that general P norm, okay? So I can take every absolute value of every element in a vector to P, whatever P is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or so forth, or 3/4, and then sum that all up and take the pth root of that number, and I have a P norm. Okay, so I can generalize this 2 norm to a P norm. One thing that has to be true for every norm is that norm has to be a positive number or a 0, and we reserve a 0 for a 0 vector. Okay? So for every other number, norm should be larger than 0. Second thing, if I multiply my vector by a scalar, I'm not doing much. Basically, the norm of that scalar times vector is absolute value of that scalar times the norm of the vector. And so-called triangle inequality has to be true. So if I take norm of x plus y, I have to be less than or equal to x, norm of x plus norm of y. So that's something, and I can construct, there's a whole science or part of linear algebra that deals with constructing different types of norms that might be useful in different applications, but these are the basic rules that they have to follow. Uh-huh.
So going back, when you say x doesn't equal 0, does that mean like it's not a 0 vector or just
For a non-zero vector, yes.
Okay.
And 0 vector is the vector that has zeros as elements.
Right. Okay.
That's a 0 vector.
Okay.
So we have defined 0 vector and unit vectors, that's any vector that has norm 1.
Okay. So
Those are our special definitions of vectors.
So what if you have like a vector like 1, -1, but it's norm 1? Isn't that negative?
No. 1 is one element, minus 1.
Absolute value.
You have to take absolute value, right? Which is why we take absolute values. Okay. So the point was here, if I have 1 minus 1, one norm of that is not 0. One norm of that is absolute value of 1 plus absolute value of minus 1. This is a great point to make here. And the norm is 2.
And imaginary numbers don't vector
They do as well. But then I would have a vector of imaginary or numbers that are imaginary numbers are actually they can be looked at as 2-dimensional vectors themselves. So you can look at them actually as matrices or the vectors that have, right? So I can define imaginary vectors as well, but we're not going to do that. Okay? Any other questions? All right, let's move on. So next thing I want to also find is like when are vectors orthogonal? Now I know if I'm again in Euclidean or regular geometry and I have a vector like this and a vector like that, so for instance 1, 0 and 0, 1, okay, they're orthogonal. Okay? There is a 90-degree angle between them. In 3 dimensions I can figure out what my angles are between vectors, but I'd like to be able to do that in general regardless of the vector. And the way it's done is by taking, this is U transpose V, assuming U and V are column vectors. And what is a U transpose V? That was that dot product. Maybe we're going to do an example in a second. Dot product of 2 vectors. And divide them by norm of 2 and norm of V. Okay. And I will define that as a cosine theta. And I will then find theta as angle between 2 vectors. So let's actually just double check that in a case where I think I know what the angle is. 1, 0 and 0, 1. So this is my U, this is my V. U transpose V is basically taking a product like this. And the way I do this product is I just go first element times first element plus second element times second element. And I keep going if I have more elements, but here I have only 2. So in this case, it's 1 times 0 plus 0 times 1, and this is indeed a 0. So cosine theta is going to be 0 divided by norm of U and norm of V. This is norm 1, this is norm 1. Either way, it's 0 over 1, it's 0. So theta is indeed 90 degrees because cosine of 90 is. So in this case, we say they're orthogonal. If I had, for instance, here 1 and 1/2, right, then I would have 1 times 0 plus 1/2 times 0, which is 1/2. So my theta would be a different angle. What is cosine of 30 or cosine of 60 is 1/2? 60. Anyway, it's one of those 2, right? Okay, so this is basically how we compute angles. So theta is angle between vectors. Oops. Oh, I did it again. Look at that. I just need to figure out how to kill it. Or remove it. Okay. And if I'm actually in 2 or 3 dimensions and I'm using 2 norm, then the angle is what we would expect it to be. Angle between 2 vectors. Okay. So this angle, if using norm 2 or L2 norm and 2D or 3D vectors, this is indeed the physical, the spatial, the angle vectors enclosed in physical space. Is my handwriting somewhat doable? This is why we mostly have PowerPoints. we already introduced unit vectors, and if I have unit vectors that are orthogonal to each other, I call them orthonormal, which was example of 1, 0, and 0, 1. So this is just definitions that you might come across. This we already introduced. And, well, if I were to convert 1 and minus 1 to a unit vector, let's see, is Jacob here, Jacob McKenzie? So Jacob, if I was to convert 1 and minus 1 to a unit vector, how would I do that? Just a quick review.
You do 1 over the L2 norm of that vector, which is 1, would be 1 in one direction.
1 and minus 1, what is L2 norm?
L2 norm of what?
Oh, 1 minus 1. So 1 over root 2 and minus 1 over root 2. All right? All right. Okay, so now we will move on to matrices. And the most fun part that we will do with matrices is matrix multiplication, and as well as matrix vector multiplication. So we will in general use uppercase Roman letters to actually denote matrices. And technically, vectors are type of matrices. The biggest difference between the two is how many rows and columns I have. So essentially, to get a matrix, I will put together a bunch of column vectors together. And I can also look at it as a bunch of row vectors together. And I will get, so matrix is essentially a collection of vectors. So we will do addition and subtractions the way you would expect it to do. So if I had two matrices, I will go element by element and add corresponding elements and get a result that is a matrix of the same size. Multiplication by scalar will work the same. So I will multiply every element by the scalar that I want. And also I will have a transpose where I will basically flip what used to be a column of a matrix, it's going to become a row, and the other way around. So let's do a couple of examples. And I will go back to this formal notation in a moment, but the best is to actually show an example. Okay. So for some reason this mirroring divider is here. So let's give ourselves a matrix A. I'm going to now switch colors. I'm tired of red. Okay. And I'm going to give myself an example. So I'm going to do 1, 2, 3, 4. And just to make fun of this, my 1, 2, 3, 4 business, I'm going to make this minus 2 just to make something different. So these are columns. So I can look at A as two column vectors. This is my first column. This is my second column. I can also look at it, in this case, as a collection of two rows. So this is my first row vector and second row. And I will refer to these positions as a row, comma, column. So basically my position A1, 1 is 1. A1, 2 is 3. A2, 1, meaning second row, first column, is minus 2. And A2, 2 is 4. So basically this first part, when I have A, I, J, this I refers to the row and the J refers to the column. So if I were to sum up two matrices, let's give ourselves another matrix B. And I'm going to let somebody here come up with a matrix. So Is Gianfranco here? Gianfranco, could you give me 4 numbers to put them in this matrix?
2,
2,
6, -4, and 1.
1. So if I were to come up with A plus B, and I'm going to call that a C, how would we do that?
Still,
Mhm.
you would just add the A11 and B11.
So 1 plus 2 is 3. So basically what I did here formally, I said that C11 is A11 plus B11. Okay? And then I would just proceed. Right? So I would have 3 plus 6, which is, so my C12 is A12 plus B12, and so forth. So let's just do this. Minus 2 minus 4 is minus 6, and 4 plus 1 is 5. Okay? So this is my result, A plus B. And then if I were to multiply with a scalar, so let's say minus 2C, minus 2C, let's meet somebody else. Logan? Logan, oh, I'm like looking somewhere. He's right there. So what would minus 2C be?
You multiply the -2 by each of those.
Each of those. So do that for me, please.
Okay, so -6, and that's a 9.
Mhm.
So -18,
Mm-hmm.
then 12, and then -10.
Okay, so this is something that we would expect. And finally, transpose of the matrix, I would flip what was a row would become a column. And the way we have to do that, the way we do that formally is basically for transpose. So if I had A transpose, then A transpose in position ij would be essentially a ji. So I would flip what rows and columns were. So this is formal way to do it. And if I was just to do it, I would just flip the numbers. So let's try with matrix A. Somebody else, Siavash. So could you do transpose of matrix A for me? What would be in this first spot?
Transposing it, it'll be 1,
Mhm.
-2 to the right, 3, 4.
So basically what was a row becomes a column, right? And the other way around. So the second row is the second column, first row is the first column, and so forth, however many I have. So those are the basic operations. Now I'm actually interested in matrix multiplication. And first thing that I will do is I will actually learn how to multiply matrix with a vector. Vector is a special form of matrix anyway. Save and open. So if I had A, my A, I will remind myself, was 1, 3, minus 2, 4. And I had a vector V, which is minus 2, 1. Then multiplication, so this is matrix vector multiplication, would proceed as follows. First thing that I will check is, can I do this? I can't always do this. So first, this is a 2 rows by 2 columns matrix, which we refer to as 2 by 2 matrix. So this is dimensions. And my vector has 2 rows and only 1 column, so it is 2 by 1. Yes?
That -1 should be -2.
Oh, good. Thank you. So I have 2 by 2 and 2 by 1. One thing that we're looking for in order to be able to do this is that so-called inner dimensions, which in this case means these two, they have to match. Or they have to be the same. Therefore, I can proceed. Okay. So multiplication can be done if inner dimensions match.
So we now will find the vector times the negative and split the order.
I could. So in this case, well, could I do 1 by 2 and 2 by 2?
Yeah.
Inner dimensions match. But if I had 2 by 1, no. So in this particular 2 by 1, these two don't match. So cannot. Okay? So basically, what will I have to do to this vector to make it work? Transpose it. Okay. So basically, I can't, yes.
So you can't put that 2 by 1 on the left side and multiply?
No.
To get a different. Okay.
You cannot do it.
Okay.
You don't have a rule to do it. Okay. So let's do it, and then we'll try to do a transpose. So in this particular case, what will I do? I will basically take 1 times minus 2 plus 3 times 1. This is why I have to have number of these columns the same as number of rows in order to be able to do this. Okay? So I'm going to say 1 times 2 plus 3 times 1. Okay? So 1 times minus 2, apologize, plus 3 times 1. And then I'm going to do the similar thing for the second row. So I'm going to do minus 2 times minus 2 plus 4 times 1. And I'm going to change the color here into this. Okay. So in the first case, it's 3 minus 2 is 1, and minus 4 plus 4 is 0. Okay. And this is a new vector. Oh, good job. I was just checking if you pay attention. That's my story, and I'm sticking to it. Oh, okay. Here you go. I'm double checking whether you're paying attention. Okay. So this is my result. So my result is a vector that is a 2 by 1, and these are those outer dimensions. So my result is 2 by 1. Okay. So the result is a 2 by 1 matrix, which is a vector. Now, if I attempt to do minus 2, 1, and 1, 3, minus 2, 4, I cannot apply the same rule, right? Because if I go to the first row, I have only minus 2, and here I have 1 and minus 2, so I can't operate, okay? So this cannot be done. But if I do minus 2, 1, and 1, minus 2, 3, 4, this is 1 by 2, this is a 2 by 2, okay? So my inner dimensions match. And I proceed as I did. So it's minus 2 times 1 plus 1 minus 2. And my second position, my position 1, 2, will be minus 2 times 3 plus 1 times 4. And I'm going to have to squeeze it. So this is a 1 times 2 by 2 vector, which is minus 4, and minus 6 plus 4 is minus 2. So this result this was 1 times 2 and 2 times 2. My inner dimensions match, so I can do this. And my result is a 1 times 2 vector. What did I learn? One parting message here is when I have matrix multiplication or matrix vector multiplication, is AV the same as EA? This is sort of the biggest hurdle in matrix multiplication. I just cannot necessarily flip things and get the same result. So my AV is not VA, okay? Does not commute. All right. Homework will be assigned today. Lots of practice of these things, and I will see you on Friday. On Friday, it will be useful if you bring your laptops. If you don't want to bring your laptops, we will have laptops for you. Just bring your UTE ID.